Hello statistics. If you're watching this video, I'm not with you. I had a ceremony at 9 o'clock at the courthouse today where I watched my granddaughter become my official granddaughter. So the adoption is today at 9, but I'm not sure how many adoptions there are and where we are in the queue and how long an adoption takes. So I just made this video in case I couldn't be with you, so you would not be falling behind. So let's pick up our class for today. It's the 5th of December already, and we're looking at our Monday edition of Stat class. All right, we'll pick it up from Friday's knowledge. We learned there that if you were taking two random variables and adding them together, we would say the total is x plus y. And we learned that the expected value of the total would be the expected value of the x random variable plus the expected value of the y random variable. So we were comfortable with that, and then we went ahead and did the standard deviation of the total, which would have been nice if we could just added the standard deviation of the x random variable to the y, but no go. So we observed through Pete and Aaron and all the who struck with the chart and everything that we could add the variances. So I'll take the variance of Pete, or x, and the variance for y, and then we went ahead and square rooted that. So we could get through the back door to the standard deviation, but we have to recall that we cannot add the standard deviations to get the total when the two are added together. So we have to go by way of the variance. Add the variances and then take the square root. So this pretty much sums up our knowledge from that. So let's see if we can use it on the back on day 4. Look on the back and you'll see where I am. Right above or beside, because we have some more notes to take from day 4 today. Alright, so we have in this situation SAT, college SAT scores, and we have the X and the Y. X being math, Y being reading. So they want the total. So go ahead, turn this off, and calculate the expected value of the total reading and math, and then the standard deviation of the total reading and math. So turn this off, and when you're ready, turn it back on and check your work. Alright, so when we found the total, we ended up just adding the 519 and the 1 up and the 507. So what's that give us? Looks like 1026. Alright, so then the standard deviation, we can't just add them. We would have to take the 115 and square it, and we would have to add that to the square of 111. And we would have to take the square root of those if they were independent. But we are saying that the math score and the critical reading score are not independent. Many times when someone does high in reading, they also do high in math and vice versa. So they are not independent events, so we cannot find the standard deviation of this total with the methods that we know. So we cannot find the standard deviation, only when the events are independent. So if you got that right, pat yourself on the back, and if not, slap your own wrist. Alright, let's put that away for now, and not away, but put that down, that idea down, and we're going to pick up another one. Take notes on it, and we're going to look at the difference between Pete and Aaron. I'm not going to develop this through the charting and all the data. I'm just going to give you the results pretty much. So it turns out when you have a difference, they were subtracting the value of Pete from Aaron. let's say we are looking for the expected value of that difference. As you might suspect, it's going to be the expected value of Pete minus the expected value of Aaron. The only warning I give is that if the order of the random variable subtraction is changed, then so does the calculation. The expected value here of y will come first, and then x. So up here it won't matter because addition is commutative, but subtraction is not. So watch the order. So I'm not going to write both of those. One is principal enough. So when we have a difference, we subtract the expected values. All right, now onward to the standard deviation of the difference. So again, we're looking at the difference x minus y for this example. So as you might suspect, you can't subtract the standard deviation of Pete minus the standard deviation of Aaron. So you're going to have to come up with another way of doing it, and it's a little bit interesting, a little bit surprising. So let me get at it, see if I can kind of at least convince you of it by saying this. We're going to look at this standard deviation is a measure of spread. So let's go back and look at a standard deviation, look at the spread of a simpler concept. Range is also a measure of spread. So the way range acts is the way standard deviation acts, and that's just the way it is. So I'm going to look at range, and I'm going to start with Pete. And I want to think of what his range was. So that means his highest possible value minus his lowest. So he could have 6 in his car, and he would only operate if 2 were in the car. So his range went from 2 to 6, which gives us 4. Now Erin's range was, her range was 5 was her highest and 2 was her lowest. So her range was 4. So now I'm going to look at the range of x minus y at the difference of the two. So what would be the highest, the highest value we could come up with if we started with one of Pete's possibilities and subtracted one of Aaron's possibilities? What combination from Pete and Aaron would give us the largest number? So to get that, by thinking of subtraction, wouldn't it be Pete's highest number, which is 6, minus Aaron's lowest number, which is 2? So wouldn't that give us the highest possible number when we're subtracting Pete minus Aaron? Is there any other combination of Pete's possible outcomes minus Aaron's possible outcomes that's greater than 4? I don't think so. So now let's think of the lowest number we can come up with. So the lowest number, and again we're starting with a number from Pete and subtracting a number from Aaron. Wouldn't we take what number would we take to get the the lowest number now? So this is the highest number possible. What about the lowest number? Can you think that out? Wouldn't we have to take Pete's lowest number and subtract from it Aaron's highest number? So 2 minus 5 gives me a minus 3. So 2 from Pete is his lowest minus her highest. Is there any way to get a number where we start with a possibility from Pete and subtract a possibility from Aaron? Is there any way to get a number below minus 3? I don't think so. So here we have the highest possible difference. Here we have the lowest possible difference. So what is the difference between 4 and minus 3? It is, if you look on the number line or you do a simple subtraction, you'll see there's 7 between negative 3 and 4. So that is the range of x minus y. But look at this. Up here we saw the range of Pete was 4 and the range of Aaron was 3. We could have just added them. And even though we are subtracting, that's the surprising part, even though we're subtracting and finding the difference, the range is still 7 as if we had added those. And that is, if you think about it, it actually makes sense because it's saying there's more variance in the combined difference of two random variables than there is in any one random variable by itself. So even though I'm combining them by subtraction, I'm adding more variance. The more I add, the more random variables involved is going to involve more difference or variance. So it's going to actually be an addition instead of a subtraction when we go to find the standard deviation. So that principle is going to follow us now to the standard deviation. So whereas you might have conjectured that it was the standard deviation of a difference is going to be, you might have said this, it's the square root of the variance of x minus the variance of y. But no, 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 it's not. It's plus. It really is. So indicate that when you have the difference of two random variables, and these again need to be independent random variables to find the standard deviation, you take the variance of the first, add the variance of the second, and then the square root. So this is surprising, but it is true. So you'll be reading about that also. So let's see what else we can say. I want to go ahead to do the next little topic. So once you got this down, I don't think I have an example right with me. I'm sure that you'll be reading some and doing some, and as you read the check your understandings, that you will exercise those. Alright, so let's go ahead then and look at what I have to finish up today. Alright, the last concept, and I have a timer going, so if it goes off, I'm going to have to shut this down and start part 2. Alright. So, alright, adding and subtracting random variables aside for a little bit, I want to discuss a normal curve. So we have a random variable that has a normal curve. Say this is x. So of course the expected value for x is right there. And say we have another normal curve. Normal curves don't all look alike, so look at this one. And it has, I'm trying to draw straight on a wiggly board. Oh well. The mean of y, or the expected value of y, is right there. So I'm going to combine these two by addition. And the difference being that we're starting with a known random variable that's normal and adding a different random variable to it that's also normal. So I'm going to look at the combination. When I do that, we're going to have a lot of spread and a little spread, so when we add each of those random variables together, we'll probably get like a medium spread. And it turns out that the mean of the combined total is going to equal the mean of x plus the mean of y, and also that total distribution is normal. So we don't have to see the data or plot it. We know if we start with two normal curves and add them, the distribution of the random variable will also, the sum will also be a normal curve. So we can write this for x and y normal. The mean of x plus y is going to be the mean of x plus the mean of y, and also, and x plus y is normal. So we have a normal curve. And the standard deviation, when we add two normal curves, is going to follow the same old rules. Take the variance of x and the variance of y, add them together, and find the square root. That'll be the standard deviation. Nothing new there, but what is new, and x plus y is normal. So I already said that. So combining, nothing's going to change in our calculations, but we can add this principle that now we have a normal curve if we started with two normal curves. All right, so why is that helpful? Well, let's do an example. Let me check the time so I don't, oh, I hear the beeper now. All right, I'm going to shut down this part and do an example, and that'll be it for today. And I'll do an example using the fact of normality.